This video is going to be about finding the pH of polyprotic acids. So polyprotic means more than one proton. So greater than one proton. So something like H2SO4 or H3PO3 or any of those acids where you have more than one acidic hydrogen in them. Usually the very first dissociation, so this is Ka1, so that means we've lost one hydrogen here. So the first conjugate base looks like that, and the first Ka is 7.5 times 10 to the negative third. And then the next one, we have one less hydrogen and an extra 2 negative charge. The next Ka is much smaller, and then the third Ka for that acid is even smaller. So every single dissociation, so carbonic acid, H2, has 2 conjugate bases here. So the first dissociation is pretty small, and then the second dissociation is very tiny. Remember, sulfuric acid is one of the weird strong acids, right? And it's weird because the first dissociation doesn't even have a K because it's so big, because it's strong, so it completely dissociates. But then the second one has a relatively high comparing to the other ones, Ka, but it's small enough to be considered weak. All right. And then we have oxalic acid and ascorbic acid, vitamin C. You can see that the Ka, so the first Ka is always going to be the biggest, and therefore the first Ka overpowers any other dissociation. So really, if you're looking for the pH of these acids, you do not have to dissociate anything else. You only have to do the first dissociation because the second and the third one are not going to matter. And I'm going to show you how the second one won't matter. But you really just have to know that this one is going to overpower everything else. So most of the stuff in solution will actually be undissolved acid because it's weak. And this conjugate base will come in next along with hydrogen. Find the pH of a 0.5 molar H2SO4 solution. Okay, so H2SO4 is strong acid, right? So when it is in water, we only dissociate one of those H's, and we get HSO4 negative plus hydronium. All right, and since we have 0.5 of this, it dissociates 100% into 0.5 moles of that and 0.5 molar of that. So what happened to my 3? I just take the negative log of 0.5, and I end up getting 0.301 as my pH. All right, and the second dissociation, because the dissociation of this is so tiny, it's not going to add a significant amount to that 0.5, and so the pH really isn't going to be much lower than that. In this problem, we need to write out the equilibria of H2CO3, carbonic acid, and water. So the first dissociation is going to be H2CO3, and water makes H3O plus HCO3 minus hydrogen carbonate. And then that hydrogen carbonate can also dissociate in water to make carbonate and hydronium. So this first one is the first Ka, so it's the first dissociation. And then the second one is the second Ka. And then we have to find the pH of 0.25 molar carbonic acid. So in this problem, I'm going to show you how to go all the way through the problem, and that it is not necessary to do so, because most dissociations are only going to be affected by the first Ka, because this number is so much larger than this one. So I'm going to prove that to you, but when you work these problems, you'll only have to do the first one. All right, so I'm going to have to use a rice table because this is a weak acid. And I'm going to have 0.25 of this. Water doesn't matter. 0 and 0. All right, and so this is going to increase on this side. And then the carbonic acid will decrease. So I'm going to end up with x squared divided by 0.25 minus x is equal to 4.37 or 4.3 times 10 to the negative 7th. All right, this x is negligible like usual. And then if I solve for x, I end up getting that x is equal to 3.28 times 10 to the negative 4th. So that is my hydrogen carbonate, and it's also hydronium from the first dissociation. So I could take the negative log of this x right now and find the pH, but I'm going to show you why that works. So in this dissociation, in the next one, I also have to do a Rice table because it's a weak acid. It's even weaker than the one before. And I'm only starting out with 3.28 times 10 to the negative 4th because my only source is right here, right? We didn't put 0.25 molar of this in the solution. It's 0.25 molar carbonic acid. So I have to start off with that. Water doesn't matter. There's no carbonate, and then hydronium also is going to start off with 3.28 times 10 to the negative 4th. So we still have to increase on the product side because we don't have any carbonate to take from, and decrease on this side. So we end up with 3.28 times 10 to the negative 4th minus x, and 3.28 times 10 to the negative 4th plus x. So I'm going to put that in my new Ka right here in my new equilibrium expression, and I end up with 3.28 times 10 to the negative 4th plus x times x divided by 3.28 times 10 to the negative 4th minus x. And that's going to be equal to 5.6 times 10 to the negative 11. This x is negligible, and this x is negligible. And then what ends up happening is these two end up canceling out. So my x value is 5.6 times 10 to the negative 11. And if I take that x, so that would be equal to carbonate. So my hydronium ion is going to be equal to, and that's what I need to find the pH, 3.28 times 10 to the negative 4th plus 5.6 times 10 to the negative 11. Now, adding those two things together is not going to change this number at all. You can try it and put it in your calculator. You're not going to get anything different. So to find the pH for this solution, all I have to do is take the negative log of 3.28 times 10 to the negative 4th, and that is going to give me a pH of 3.48. So that's my answer. And that's it. So you rarely have to do these, and in AP Chem you don't have to do them ever because this Ka is going to be so much smaller than this, and the concentration will not make it to where this Ka is affected.